In this section, we're going to look at applications and models. Exponential and logarithmic functions are important in many areas, and this is one of the chances that we get to see where the stuff that we're learning is actually used. If you were a city planner and needing to plan for what the population is going to be 20 years down the line to look at the roads and the water sources and stuff, you would use a population growth um, formula. The population growth formula is P of t equals P sub 0 times e to the kt power. The P of t is going to stand for population after time. The P sub 0 is the initial population. The K is going to be the growth rate, and remember this needs to be in decimal form. Anytime you're taking a number from a percent to a decimal form, you're going to move the decimal to the left 2 places. So 2% would be 0.02 in decimal form. The T is going to stand for just the time. The E, of course, is our new irrational number, which is approximately equal to 2.718. Another important formula that we're going to use is doubling time. The doubling time is T is always going to equal the natural log of 2 divided by K, where the T will just be time and the K again is going to be the growth rate in decimal form. Let's look at where we can actually put these into play. Under ideal conditions, a type of bacteria has an exponential growth rate of 16.7%. Suppose 50 bacteria cells are placed in a test tube. Find a function to model the population growth after t days. So we're going to say the population after time is going to equal the initial population. The initial population is going to be 50 of those bacteria cells times our new number e raised to the kt power. The k, or the growth rate, is going to be 16.7%. So in decimal form, that's going to be 0.167 times our t. That would be the actual formula we'd use for this problem. To see how many cells will exist after 10 days, we're going to say the population after 10 days is going to be 50 times e raised to the 0.167 times 10 power. Let's actually look at that on a calculator. To plug that in, we're going to type our 50 times our e, which remember is going to be the second ln, raised to the 0.167 times 10 power. Now notice all of that's in an exponent, so it needs the whole exponent needs to be in parentheses. And that's going to be approximately 265.6, or if we round to the whole numbers, 266 cells. To find the doubling time, remember that the doubling time is always going to be the natural log of 2 divided by our growth rate, or in this case, it's going to be the natural log of 2 divided by the 0.167. So if we plug that into our calculator, the natural log of 2, closing the parentheses, divided by the 0.167, the doubling time for this bacteria is going to be 4.15 days. Now, let's go ahead and look at another model. If we have interest that is compounded continuously, that formula is going to be P of t equals P sub 0 times e to the kt power. That should look a little familiar. In this case, the P of t is going to be the amount of money after time. The P sub 0 is going to be the initial amount of money invested, which is just the principal. The K is going to be the interest rate in decimal form, and the T will be the time in years. So let's look at an application for this. Suppose $5,000 is invested in a CD at an interest rate of 4.25% per year, compounded continuously. To find the function to model the amount of money after T years is going to be the amount of money after T years will equal the initial principal, which in this case is 5,000, times E raised to the K, and the K is the interest rate. Remember, this needs to be in decimal form, so that's 0.0425 times T power. How much money will be in the CD after 5 years and after 10 years? So we need to find the amount after 5 years, which will be 5,000 times E raised to the 0.0425 times 5 power. After 10 years, we're going to use the same formula. P of 10 equals 5,000 times E raised to the 0.0425 times 10 power. So now all we need to do is punch these into our calculator. For the first one, I'm going to put 5,000 times my E raised to the 0.0425 times 5 power, and that's going to give me $6,183. And remember, with money, we're always going to round to the hundredths or the pennies place, and 83 cents. To do it for 10 years, we type in the 5,000 times our E raised to the 0.0425 times 10 power, closing our parentheses, and after 10 years that will have grown to $7,647.95. The doubling time, remember, is going to be doubling time always equals the natural log of 2 divided by our growth rate. So in this case, we're going to have the natural log of 2 divided by 0.0425. On our calculator, punch the natural log of 2, remembering to close the parentheses, divided by that rate of 0.0425, and we'll get, after 16 years, about 16 1/3 years, will be the doubling time for this investment to go to $10,000.